We have been looking at classification and in particular classifying images. When we trained, we looked at the accuracy of the training. And after some basic testing, we were able to see that our neural network was able to recognize things pretty well. But this might lead you into a false sense of security. And I'd like to explore some of these issues around this with some methods that you can use to avoid errors in training your neural network naively. Imagining a scenario where you want to train a neural network to recognize shoes. It's like teaching somebody who has never seen a shoe before what a shoe actually is. So that in the future, when they see an object, they can decide whether they are seeing what they're seeing is a shoe or not. We know that there is a huge variety of shoes, and there's no hard and fast rule as to what makes a shoe a shoe. Typically, the steps that you would like to follow are to get as many examples of shoes as possible. Train a network using these examples and then profit. Earlier, you trained a neural network to recognize handwriting images, and it needed 60,000 examples. There's a lot of shoes that you're going to use, but how are you going to find all these shoes, right? But you have to gather as many shoes as possible and train by looking at them. And you might end up with something like this, an increasing accuracy number as you train. By the time it finishes training, it has a high accuracy. Maybe even 100%. You might think you have written an amazing AI that can recognize shoes. It's time to profit. But then you show it a shoe like this and it fails. You thought you were 100% accurate in recognizing shoes, but the reality is that you were 100% accurate in recognizing the types of shoes that you trained the neural network on, and that 100% led you into a false sense of security. Your perfect neural network architecture might not be so perfect after all. There's a number of ways to help prevent this, and we'll look at the simplest first. Consider your shoe scenario, where we had a lot of shoes, and we can represent them using this yellow rectangle. We use all our data to train our network. Why not? The more we train with, the better, right? In principle, this sounds fine, but we have no way of testing it against previously unseen data because we used all our data to train it. So what if we hold back some of our data? Don't train on all the data, save some for validating that neural network as we are training as well. By having this set that we can then use to measure how it does with unseen data. We can represent this with the red rectangle. The full data is the same, but the training data is now smaller. It's a full set minus the validation set. And then take this a step further. How about holding back a little more so that we can then use to test our network after it's done training? Our first subset, the yellow rectangle, is data we'll train with. The second subset, the red rectangle, is the data that we'll use to validate the training by testing after each step how the network is doing and not using this data to train the network. Our third and final subset is the blue rectangle. It's used as a clean set to test the network after we are done training it. Following this methodology, we could, for example, pick a neural network architecture and train it. On the training data, it's 99.9% accurate, but it does worse on the other two sets. It's only 80% on the test set. This could be like our shoe scenario earlier. We've designed a neural network that is great on our training data, but is not so great on other data. Our 99% makes us think we have a much better network than we actually do. So we redesign our neural network architecture and try again. Our accuracy on training might go down, but what's most important is keeping the accuracy of the network on the training data as close to the validation and test data as possible. This gives us a true signal of the real accuracy of the network. Returning to our code we've been using to train MNIST handwriting digits. Recall that we had training images and labels and validation images and labels in our data set. We could load them with one line of code in TensorFlow. But when we trained, we just used the training images and labels. And we could see our accuracy epoch by epoch. It got to 97.5% in just 20 epochs, and that's pretty good. But it's just on the training data. We have no context of how good or bad it is with previously unseen data. So we can update the model.fit validation to use the validation data like this. And when you train, you get reports on the accuracy of the data on the training data, step by step, as well as the validation data. I've highlighted them in this diagram. And while the accuracy of the training data gets up to 97.59%, the accuracy on the validation is at 96.26%. They'll almost never be the same, and your goal is to strive to get them as close to each other as possible. This is a sign that your neural network is good at generalizing and not over-specializing to the training data. If you have the test set, MNIST doesn't include one, but other data sets do, then you can perform model.evaluate on it after training is complete to see the results. And you'll get an accuracy value for that. You'd expect it to be similar to the validation one, or maybe a little lower if your network is well architected. Your confidence in your network's ability to classify should be based on this value. Now that you've looked into classification and understand how to train with split data sets, we'll have a quiz soon to test you on what you've learned so far.